Hello, good morning everyone. Today we will be starting with the third unit, that is the deflection. So first of all I will tell you what is deflection. Deflection, suppose we are having beam here and it is simply supported, okay, and when we are applying a load here, suppose we are applying P load, so after the loading it will try to bend the beam like this, okay, so it will try to bend the beam like this. So this is the deflection. This is the what in the vertical direction, the beam which is going in the vertical direction, that term is denoted by y, and this is known as the deflection. Here it has been written that the beam member, when subjected to load, transverse load, I am talking about the transverse load, there will be some vertical deformation which is called deflection, okay. So this term is known as the deflection when the axis of the beam moves in the vertical direction. So this axis of the beam is moving in the vertical direction, so this is known as the deflection. So you can also term it as that the displacement of point from the initial position to the final position in the elastic curve is known as the vertical deflection. So you can also term it as the displacement of one point from its initial position to the final position in an elastic curve, that is also known as the vertical deflection. So before going into this topic, I want to tell you that nowadays we are designing any structure where we have to see that it is having two criteria, that is, one is the strength criteria and one is stiffness criteria. So in case of a deflection, first of all what you will see, the amount by which the beam is getting deflected. So beam, suppose we are talking about I am taking an example of a beam here. So when we are talking about the beam, so beam deflection, this deflection depends upon what? So first of all you will say that it is depending upon the cross sectional area, how much amount of loading is there, you can say the bending moment, how much bending moment is there, how much shear force is there. So these are the criteria for governing the deflection. And now when I am saying that when you are designing any structure, so first of all you have to see two criteria. One is, first of all you will say that it is having one strength criteria, okay. Second one is stiffness criteria. So this is the stiffness criteria here. So these two criteria are the main thing that you need to consider when you are designing any structure. So what comes under the strength criteria? First of all, when you are designing, for example, we are taking any beam, so it should be strong enough to resist the moment, that it can resist that moment and shear force for which we are designing that beam. So that comes under the strength criteria, that it can that it is strong enough to bear that loading, that moment, that shear force, or the while in case of the stiffness, when we are talking, it is in that case the beam should be stiff enough, that it should be stiff enough to resist the deflection. So when I am saying this, that it is case of a deflection. So deflection is that thing, if his beam is bending, or you can say beam is deflecting more than, suppose we are having this beam, okay, now I am taking this example, and we have a limit of this beam that it can deflect only for y up to this mark, okay. So the permissible amount of deflection is, suppose we are saying that 0.1 mm is allowed and it is deflecting more than this, so there is a deflection is more than the permissible limit. In that case this structure is failing. So you have to see both the criteria, that it is obeying the strength criteria and it is obeying the stiffness criteria. So for designing any structure you have to see both the criteria. Strength criteria is based upon the how strong the structure is, and stiffness criteria is based on the how stiff the structure is to resist or to resist that deflection, that it should not allow more than deflection than the permissible limit. Okay, so this is the stiffness criteria and strength criteria. So when we are talking about deflection, so we are talking about deflection here. So I hope you are getting the point that deflection is a vertical displacement when we are talking about vertical displacement. And now the term comes, the multiple girder bridge is designed based on the strength and stiffness criteria both. So I have told you this part, that when we are designing any structure, we have to see both the part, that it is obeying the strength criteria also and it is obeying the stiffness criteria also. So this is why we are seeing both the criteria. For decreasing the deflection stiffness of the beam material is increased. When we are talking about the stiffness and when there is a more deflection in this beam, for example, what you will do, you will increase the stiffness of the beam material is increased. For decreasing the deflection, what you will do, you will increase the material. So this is the criteria that we will talk in deflection. So first of all, the terms that you must be familiar with is the deflection. Deflection is denoted by y here. Y is the deflection, and when we are talking dy by dx, it is the slope. And ei, that is flexural rigidity, into d square y upon dx square is equal to moment. And you know that when we are talking about shear force equal to this thing, I have already told you when we were doing the in strength of material, when we were learning the shear force and bending moment diagram, that V is equal to dm upon dx. And when we are talking about load intensity, that is dv by dx. From here, when you know the moment equation is this, and V equation, V is shear force is equal to dm upon dx, so it will be ei d cube y upon dx cube, that is equal to shear force V, and ei equal to d4 y upon dx4 equal to load intensity. So these are the terms that you must know. Now the most important part before going to the deflection is the moment curvature relation. This is the moment curvature relation. So how we derive this equation? That is based on the moment curvature relation. So for that, I have taken an example of this. Suppose we are taking an example of this simply supported beam, for example. Okay, when the loading is here and it tries to bend the structure like this, the beam bends like this. So I am taking a small part here of the beam which is deflected, that part is ds. Okay, when we are taking this small length of the structure, so here I have taken a small length ds. Okay, this is the length AB. From A is this point, B is this point. From A to B, the length is ds. This is the small part of the beam which is deflected. So ds you can say is the small length of the bent beam considered. Okay, and r is the radius of curvature of the beam. So radius of curvature means when we are talking this point, so suppose it is meeting here somewhere here, that is C point here, that is C point, center of the beam. So when we are talking about this part, small part, so this is the radius of curvature. So it will make an angle because it is bending. So bending will produce a slope here. Slope will this will having some radius of curvature also. So I have defined that the point from where we are taking the radius of curvature as C, that is the center for the bent beam, this arc. So I have taken this arc. So for arc length is R here, and this angle is D psi. And from A point, when we are taking one point of this length is A and other point is B. So from A, when you are making an angle with the horizontal as psi, and from B it is making an, this is, we have dropped a tangent here. This is very small bend. Okay, this is very small bend because we have taken a very small part here. So from here, now C is the center for the bent beam arc. Okay, and R is the radius of the curvature of the beam, and psi is the angle made by the point A of beam with the horizontal. This is the angle made with the horizontal, and psi plus d psi is the angle made by point B of the beam with the horizontal. This is the angle made by B point. and d psi is the angle made by the beam AB with respect to the center. Here we have taken d psi, the angle that is made with the center. Now we come that angle ACB equal to d psi. I have denoted this is A point, this is C point, this is C point. So angle ACB is d psi. So we know that the length of the arc is AB. I have taken a length of the arc is A and B, and AB length is given as ds, small length, that is ds, and that can be denoted by angle into radius of curvature. That you can calculate the length of the arc as angle into radius of curvature. I hope you know this point. So d psi into r. From here we will get that 1 upon r equal to d psi upon ds. This is the first equation. Okay. Now we are considering the angle ABD. Where is the angle ABD? This is the angle A. This is ABD. This is the small triangle. When we are taking triangle ABD, this is the triangle. And in this triangle, this side is dx and this is dy. This is very small. Okay, so we have taken add dx, and this is in vertical direction, it is dy. So when this is psi, so this angle which we are talking about, this angle will be also d, when it is psi, so it also will be psi. So in this triangle ABD, I have taken this angle also psi. So this is dx and this is y. I hope this is clear. And the length of the arc is ds. So we are assuming it at straight because it is a small part, arc length, small, very small arc. So now in this triangle, from this triangle we will get tan psi equal to perpendicular upon which, that is dy upon dx. So let it be second equation. Here we can calculate cos psi as dx upon ds. This is third equation, and from here we will be using these parts in further derivation. So I have taken 1 upon cos phi equal to ds upon dx, and 1 upon cos phi will be sec y psi. So sec psi equal to ds upon dx. This is the fourth equation. Now we will be differentiating this equation, second number equation, with respect to s. So we will get tan psi differentiation will be sec square psi, and psi differentiation will be d psi dx, because we are differentiating with respect to x here. So psi differentiation will be d psi upon dx, and equal to the term was dy upon dx, and again differentiating will give it second derivative, d square y upon dx square. So I hope this point is clear. Now what I have done here, sec square psi dot, I have just separated these two terms. D psi is here, now dx is here. I have just multiplied and divided by ds here. Just multiplied and divided by ds here. So that is similar equation now. Now from here what you have, ds upon dx, and that from equation 4th you can see ds upon dx can be written as sec psi. So from sec psi into sec square psi will be sec cube psi into d psi upon ds. The equation will remain same now. Now from in this term d psi upon ds, you can see that first equation was d psi upon ds. This term, this one, is equal to 1 upon r. So I will replace that here. So d psi upon ds is equal to now sec cube psi into 1 upon r equal to d square y upon dx square. This is from equation 1. Okay. Now I have put this term here, and this will go downwards in dividing this. So d square y upon dx square will be divided by, now what I have done, it is sec cube psi. So I have just put the value sec square psi into cube upon 2. So 2 and 2 will cancel out, and it will give sec cube psi. Okay. So for easy calculation I have just done this part. The sec square psi will be 3 by 2. Okay. Okay, I hope this point is clear. Now from the identity of tan and sec, I can put that sec square psi will be 1 plus tan square psi. So I am just replacing the trigonometric identities here. 1 upon r equal to d square y upon dx square. So 1 upon sec square psi will be 1 plus tan square psi, and tan square psi you have already calculated that tan psi will be from equation 2, that it will be dy upon dx. Now I will replace tan square psi will be dy upon dx whole square. Now what is dy upon dx? That is the slope, and slope is very small. The denominator is very small because we are talking about the arc, that is the very small length. So angle will be very small. So dy upon dx is the slope and it is very small, so we will be neglecting this term. So this term will going to be 0, and 1 upon r will be this term only, dy upon dx whole square, this term will be 0, and this is 1 plus, so that will not be infinity, that will be this divided by 1, so that term will be 1 upon r equal to d square of y upon dx square. This is the fifth equation. Now when you know this point, and when you reach this point, now it is very easy. From the flexural formula that you have studied in strength of material, that m upon I equal to sigma upon y equal to E upon r. So from here I can use this equation, m upon I equal to E upon r, and I already know that I will replace this E here, and it will be equal to 1 upon r, and 1 upon r is already I know that it is equal to d square y upon dx square. So I have put that 1 upon r equals to m upon ei equal to d square y upon dx square. So I can use this formula now. So from here I can use m equal to ei d square y upon dx. So this is the moment curvature relation, and with this we derive the moment curvature equation, and we will be using in the various methods. There are various methods to calculate the slope and the deflection. I hope this point is clear. So this is the very important equation that we have derived. You must go through this, and I hope all the points are clear, that we are learning about deflection here. So I have taken a small point of the deflected beam, just a small arc of the deflected beam here. So now when we have derived this equation, we can easily derive this equation for shear force and load intensity. And when we want from moment equation, we want the value of the slope, how will you do? We will be integrating. When we are integrating this equation, we will get, because integration of d square y upon dx square will give you dy upon dx, and that will be equal to slope. So this is the concept behind the deflection. Thank you very much.